Nope.
Okay, thanks everybody for coming. This is the first talk of the semester. We have Nathan Wagner from WashU, and he's going to talk about mapping properties of the Bergman and Cauchy-Szego projections.
Thanks, Chris. I appreciate the invitation to talk here. I apologize in advance. I'm actually waiting on a call about my car today, so there's some possibility that they'll call, of course, during the presentation, and I'll have to step away for a minute, but hopefully that doesn't happen. But I just apologize in advance if that does occur. So yeah, I'm going to talk about mapping properties of the Bergman and Cauchy-Szego projections. This largely is going to be an expository talk, but I will mention a couple of results towards the end that are joint work with Brett Wick, who is my thesis advisor. Okay, so let's get started talking about these function spaces. So we're working in several complex variables. So giving a domain D and Cn, we can define the Bergman space A2D to be those holomorphic functions on D that are square integrable. And here dV is just Lebesgue measure on Cn, which we can think of as R2n. And so these are holomorphic functions on the domain that don't grow too much during the boundary so that they are still square integrable. And you can show using the mean value property for holomorphic functions. So that says that if I have a holomorphic function, the value at the center of a ball is equal to the average of the function on that ball. So you can use that plus Holder's inequality. And that will basically give you that the pointwise values of your function are controlled by the L2 or A2 norm, which would just be the square root of this quantity above, the usual 2 norm, on a compact set. And so then you can show that you have like uniform convergence on compact sets, and that gives you that A2 is a closed subspace of L2. So since L2 of D, of course, is a Hilbert space, and I have a closed subspace of a Hilbert space, I just know from Hilbert space theory that I can form the orthogonal projection from L2 to A2. And this is called the Bergman projection, and we'll denote it by this calligraphic P. And it's also true that the function space, the Bergman space, is what we call a reproducing kernel Hilbert space. I didn't write out the definition here, but that means that point evaluation is a bounded linear functional, as many of you know. So this means that the Riesz representation theorem guarantees the existence of what's called a reproducing kernel function. That's this BD-ZW, and that's called the Bergman kernel. And it turns out that the Bergman projection can be represented exactly as integration of your function against this Bergman kernel. And that makes sense, right? Because if I feed in a holomorphic function, we know that the reproducing kernel reproduces functions in the space. So then I recover the function. And you can actually show that this coincides to the operator D. So importantly, I have an integral representation for the Bergman projection. Okay, so now I'll talk about the case when it's on the disk, just because I know a lot of folks here are probably more comfortable with the disk, maybe don't do things in several variables. So if we look at the case where n equals 1 and D is just the unit disk in one dimension, we can define this as sort of a weighted Hardy space, which may be something that folks in this seminar are more familiar with. So A2 in this case is given by functions that are holomorphic on the disk and have power series representations so that this condition on the Taylor coefficients holds true. So if you look at the summation of mod an squared divided by n plus 1, I require that sum to be finite. So it's sort of a weighted Hardy space in that sense. And many of you may have seen this as well. So we can explicitly compute the Bergman kernel for the disk, and that's what it is. I'll mention that the Bergman kernel for the unit ball in Cn is basically what you would expect it to be. Instead of a 2 in the denominator for the exponent, I would have an n plus 1, n being the dimension, And then in several complex variables, I can't exactly multiply complex numbers, right? Because they're vectors, not scalars. But I would replace this W bar Z by an inner product. And in fact, sometimes people still write W bar Z even in several complex variable notation, but they're meaning the inner product. So, okay, so that's the Bergman space. So let me talk about Hardy spaces. So I think probably everybody here is familiar with the Hardy space on the disk, but I'm going to start by sort of defining a more general notion of a Hardy space on a general domain. So if we have a domain in Cn, we can define a Hardy space this way. So we look at the following closure, which is taken in the L2 norm of the boundary. And what we look at is the set of those functions which arises boundary values of functions that are holomorphic in the interior and continuous up to the closure. And then we take the closure of all of that in L2. And if you do this for the case of the disk, you would get the usual Hardy space. So again, well, this time just by definition, we have a closed subspace of the Hilbert space, so we can form an orthogonal projection, which I'll denote by a calligraphic S from L2 to H2. And that's called the Cauchy-Szego, or simply the Szego projection. And this operator also has an integral representation. So this function SD of ZW is called the Szego kernel. And here we're going to be integrating on the boundary. So mu is Lebesgue surface measure on the boundary. And I'll just say briefly, this is a little bit technical because you're dealing with boundary values of things. So as you're probably familiar, there's a way to go back and forth between boundary values of a function and interior information about the function through the Poisson integral. So I can identify functions on the domain with the boundary values. And so this integral actually makes sense if, as a bona fide integral, if Z is in my domain, and then I'm looking at sort of the interior values of the associated Poisson extension. If Z is on the boundary, then you have to interpret this as some kind of singular integral. But I won't belabor that point too much. So again, I think everybody is probably familiar with this, but I'll just review the case where n equals 1, we're in one complex dimension, and the domain is the unit disk. Again, I think probably everybody knows this, that the Hardy space is those functions holomorphic on the disk whose Taylor coefficients are square summable. And the Szego kernel, which again, I think everybody has seen, probably is given, sorry, that should be an S there, not a B. I always find typos in the midst of doing a talk and not before. But yes, this is the Szego kernel for the disk. And it's the same as the Bergman kernel, except instead of a 2 power there, you have a 1. And you can compute this directly, for example, by using the formula that if you have an orthonormal basis Fn, then you look at the summation of Fn of Z, Fn of W bar to get your reproducing kernel for a reproducing kernel Hilbert space. Okay, so a lot of what I study is the mapping properties of these operators on various function spaces. So it's immediate just by the definition that the Bergman and Szego projections are bounded on L2. That's because they're defined as projection operators, right? And it's of interest to determine whether the Bergman and Szego projections extend to a bounded operator on LP. So this is a question that often in harmonic analysis, which is sort of part of my background, we look at integral operators and then try to determine LP boundedness. For someone that's more interested in function theory, you might say, why would you care about LP boundedness? Well, here's an example of an application. So it turns out that if the Bergman projection is bounded on LP, then that means that the dual of AP is AQ, where Q denotes the Holder conjugate, and that's sort of what you would expect. So I didn't define AP spaces, but they have the same definition as A2, except you look at the P norm rather than the 2 norm. And so the boundary geometry of the domain D bears heavily on answer to this question. And we'll see later there are sort of nice domains where you get LP boundedness in the full reflexive range. But then there are certainly domains that are not as nice. Okay, so let me first talk about the boundedness of the Bergman projection on the ball, which is sort of the simplest domain we can think of in CN. And if you want to think about it for the disk, then that's just the ball. That's the same as the ball in dimension 1. So this was proven by Rudin and Forelli in 1974. I'm not sure if it was known before, but I think that this is sort of the proof that everybody references. And two key ingredients in this proof are Schur's test for integral operators with positive kernel and what's referred to as the Rudin-Forelli estimates. So I'm going to briefly talk about both of those without actually going through the whole proof. And this is sort of just a side note, but it turns out that proving things in this way gives LP bounds for the integral operator with this kernel. And so instead of the Bergman kernel, we have the absolute value of the Bergman kernel for the ball. And you might call this the positive operator associated to the Bergman projection. So if you prove bounds for the positive operator, it's pretty easy to see that implies bounds for the Bergman projection itself. And this is something that's interesting about the theory of these operators, is that usually, I guess in every case we know the boundedness of the projection, the ordinary projection, is equivalent to the boundedness of the positive operator, which is kind of interesting. Okay, so let me talk about what Schur's test is. So it's a test on integral operators. So you have some measure space, x comma mu. P is between 1 and infinity, and P and Q are Holder conjugates. So if we have a non-negative kernel h of xy, we can define this integral operator as integration against the kernel h. And so what Schur's test says is if you have a positive function h on x, which is often referred to as the test function, and a positive constant c, so that these bounds hold. So what this says is if I integrate h to the q, that's controlled above by a constant times h to the q, where so basically when I integrate against the kernel, it returns the function, or it is bounded by a constant multiple of the function. And then there's sort of the adjoint statement that the same is true when you replace integration in y by integration in x. And what Schur's test says is if this happens for almost all y and x, then the operator t is bounded on LP x mu, and you can in fact estimate the operator norm and say it's less than or equal to c. So I didn't write out the whole proof of this because I have a lot of things that I'd like to talk about, but let me say just briefly in words kind of how this works, and maybe you'll at least believe me that something like this could work. So the proof is simple in the sense that it only uses basically Holder's inequality, but you need to sort of apply it in a clever way, right? So if you want to estimate the LP norm of the integral operator, then you're integrating this quantity to the p, absolute value of that to the pth power. So first we can go ahead and estimate the absolute value of this guy to the pth power. We can crash through with absolute values. And then we're going to apply Holder's inequality by writing the kernel as h to the 1 over p times h to the 1 over q, because 1 over p plus 1 over q is 1. And then we'll also introduce the test function h. And I think we'll do that by writing h to the 1 over p times h to the minus 1 over p or something like that. And then you do Holder's inequality appropriately, and you'll get two factors. One factor is going to be controlled using the first condition, okay? And then you'll have this times the other factor, which then you need to integrate. and then you use Houdini's theorem, and then you use the other condition, right? So it's it takes some doing, but hopefully you at least believe that something like that would prove this result. Okay. Okay, so the second piece of this proof that Rudin and Forelli used is called the Rudin, often called the Rudin-Forelli estimates. So basically, this estimates integrating quantities like this over the ball, and you notice that this quantity in the denominator is like the Bergman kernel. I have the n+1, but then I also have this plus c plus c. And so if we suppose that c is real and t is bigger than 1, then this integral has the following asymptotic properties. If c is less than 0, then it's bounded on the ball. If c is equal to 0, it behaves like the log of 1 over 1 minus mod z squared as mod z approaches 1 from the left. And if c is greater than 0, then it behaves like 1 minus mod z squared to the negative c as z approaches 1 from the left. So this is, the third one is the one we were going to use. And maybe you can see how that would marry nicely with Schur's test. Because what I'll want to do is, for my test function in Schur's test, I'll take some appropriate power t of this radial function, and it's going to be a negative power, because then I want t minus c to be 0, because this is just, I just want this to be the Bergman kernel, right? So then t would equal minus c, okay? And then this says that if I integrate this, I essentially get the function back, right? I get 1 minus mod z squared to the minus c. And that's exactly what is needed for Schur's test. So again, I know this is a little bit hand-wavy. I didn't write out all the details, but maybe you can believe that this would prove the boundedness. Okay. So let me talk about the boundedness of the Szego projection on the circle. I'm not going to really give a detailed proof, but I'm going to sort of justify, in a sense, why it's true. So, and the reason is basically that it's related to the Hilbert transform on the circle, and the boundedness of the Szego projection is equivalent to the boundedness of the Hilbert transform on the circle, which is well known to be bounded on LP. So I'll sort of just reference that result. But so if we write a function on LP of the circle as a Fourier series, which we know we can do, we can then define these operators P plus, which is sometimes called the Riesz projection, and is actually the same thing as the Szego projection, and P minus. And to be careful, we may want to define them to start on trig polynomials or on L2, but that's not a big deal. They'll extend to LP. So for P plus, we look at only the non-negative Fourier coefficients, and for P minus, we look at the negative Fourier coefficients. And as I said, the operator P plus is exactly the Szego projection. And then the Hilbert transform, which is also the harmonic conjugate operator. So it gives the harmonic conjugate of a function. And it's defined by HF equals 1 over I times P plus F minus P minus F minus 1 over I F out of 0. But then you can express P plus in this way as 1/2 times I HF plus F. So that's just the identity operator plus F out of 0, which is just going to be the 0th Fourier coefficient, of course, is just the integral of the function on the circle. And so then you can basically appeal to the fact that the Hilbert transform is bounded on LP, and that will show you that P plus is also bounded on LP. So basically these relations tell you that the boundedness of the Szego projection is on the circle is equivalent to the boundedness of the Hilbert transform on the circle, which is well known. And so I won't go through a detailed proof, but that's kind of the idea. Okay, so that was in sort of in, well, n dimensions in the ball in the case of the Bergman projection, or just on the circle in the case of the Szego projection. But what about domains and several variables? What types of domains do we want to look at? So when we're studying the mapping properties of these operators, it makes sense to restrict to a special class of domains that are called pseudoconvex. And this is a very useful notion in several complex variables. So if D is a bounded domain in Cn, we'll say it has C2 boundary if there's a C2 function, and we're going to call this a defining function. And this function rho is going to go from Cn to R. And the domain is going to be equal to the set of Z where rho of Z is less than 0. And we also require that the gradient of rho is non-vanishing on the boundary. So an example for the ball, a defining function would be rho of Z equals mod Z squared minus 1. And I guess you can deduce that a bounded domain of certain smoothness must have a defining function of certain smoothness using something like the implicit function theorem. And if you have a defining function, it's not necessarily unique, but that is never really a problem in practice because you always like prove things are independent of the defining function. So for the ball, this would be a defining function, right? Because the ball is defined to be the set of points where mod Z squared, the complex component squared is less than 1. And so inside the ball, this is going to be negative, right? And so that would give us the ball. And so a way to define pseudoconvexity and respectively strongly pseudoconvex is that if for each point P in the boundary, what's called the Levy form, which is this matrix of mixed derivatives, partial derivatives, second partial derivatives, is positive semi-definite or respectively positive definite in the case of strongly pseudoconvex on the complex tangent space. So that's kind of an ugly definition if you're not familiar with several complex variables. I find a helpful way to think about these domains is that they're precisely the domains of holomorphy in Cn. So that means that there exists a holomorphic function on this domain that cannot be analytically continued past the domain. So this means that in some sense, these are the right domains to study. And certainly for studying mapping properties of the Bergman and Cauchy-Szego projection, you want to be looking at domains of holomorphy because otherwise you could just extend your functions and then you could get trivial estimates on the Bergman and Cauchy-Szego kernel. And this is only a useful definition when my domain is bigger, is dimension bigger than 1, because it turns out that in dimension 1, every domain is pseudoconvex. So this is a useful definition only in several complex variables. So let's just talk about what's been established for the LP regularity of these operators on various domains. So in the case of the Cauchy-Szego projection, we already talked about this when the domains, the disk, or I guess the circle, if we're looking at the boundary, this was done, I guess, first due to Emmerich, and it's a classical result. The Bergman projection, as I said, was done for the ball by Rudin and Forelli in 1974. Okay, and so the next big advance was for strongly pseudoconvex domains with smooth boundary, and that was done both for the Bergman and Cauchy projection by Fong and Stein in 1977. So for the Bergman projection, again, they basically use Sugar's test. So this is used very often. You know, you have some estimates on the kernel, and you integral estimates on the kernel, and you use like a type of Sugar's test. For the Cauchy projection, they use the kind of singular integral theory, and in particular, singular integral theory on the Heisenberg group, I believe, to prove their results. And so past this, there have been some more results. So for the Bergman projection, you can actually prove the boundedness for more domains. So these are all smoothly bounded pseudoconvex domains, but they're not necessarily strongly pseudoconvex. But we still have some information about their boundary, and that the boundary geometry is kind of nicer. And I'm not going to get into the weeds with the formal definitions of all these types of domains, but basically think about the boundary geometry kind of being simpler. And so it was done in the case where D is what's called convex finite type, decoupled finite type, and pseudo-convex finite type in C2. And all these were smoothly bounded. And that was done by Jeff McNeil in 1994. And what's interesting about his proof is that it actually uses singular integral theory, which we'll talk about later, and views the Bergman projection as a Calderón-Zygmund singular integral operator, in contrast to Schur's test. Okay, and then sort of a different direction you can push it is, instead of looking at other types of pseudo-convex domains, you can look at strongly pseudo-convex domains and really push the smoothness. So Lanzani and Stein did this in the case that D is strongly pseudo-convex of class C2, which is the minimal smoothness case, because if you notice, our definition of strongly pseudo-convex involved two derivatives of the defining function. So to even make sense of that, you need your domain to be C2. And the proof, again, does use Schur's test for the Bergman projection, in a sense, and it uses what's called the T of 1 theorem for the Szego projection. For those of you that aren't familiar, the T of 1 theorem is really important in harmonic analysis, and it's a test on an integral operator that basically guarantees that the operator will be bounded on L2. And then they prove that the operator is sort of a generalized Calderón-Zygmund operator. And we'll talk a little bit more about what that means later. But their technique also uses a lot of complex analysis and operator theory. And in particular, they use this theory of holomorphic integral representations in several complex variables. So it turns out that you can sort of construct integral operators that reproduce and produce holomorphic functions in several complex variables. And these operators won't be necessarily equal to the Bergman projection or the Szego projection, but they can be related in some appropriate way, in that sort of the error between them is sort of small. And so they're actually not studying the Bergman and Szego operators directly. They're kind of studying a family of these other operators. But I won't get too much into that because I think that would lead us too far afield. So let's talk about, so this is kind of interesting. So I talked about, you know, where do you have the good behavior? You know, where are these projections bounded on the full reflexive range from P between 1 and infinity? But you have sort of bad domains where that isn't the case. So an example, just in the plane, if you, in one dimension, if you think about a Lipschitz domain that has corners, it turns out that these projections are bounded for a limited range. And this is again a paper by Lanzani and Stein, and it's really interesting because the range of exponents for which the projection operators are bounded depends on the Lipschitz constant of the domain. So I think that's pretty interesting. And there's another example in two complex variables. So if you look at what's called the Hartog's triangle, this is a famous source of pathologies in several complex variables. So it's defined to be the set of Z and C2. So that's Z is an ordered pair, Z1 and Z2, where mod Z1 is less than mod Z2 is less than 1. And it turns out the Bergman projection is bounded on LPH only for P between 4/3 and 4. And that's known to be sharp. So that's kind of interesting. The Hartog's triangle kind of has a bad singularity at the origin that's kind of causes these problems. And so Luke Edholm and Jeffrey McNeil actually did more work on this and studied what they called generalized Hartog's triangles. So you can take a parameter gamma in R plus and look at this domain. And so it's the set of Z and C2, so that Z1 to the gamma is less than mod is less than 1. And it's pretty amazing that if gamma is irrational, then the Bergman projection is bounded on this LP space only for P equals 2, which is like the trivial one, right? Because that's just guaranteed by definition, and it's not bounded for any other P. So that's kind of a crazy result, I think. that if gamma is irrational, that happens. So that's just some examples to show you that you can have more pathology. Okay, so let's talk a little bit about singular integral operators, because these are going to be connected to our study of the Bergman and Szego projections. So singular integral operators are really important. They're a fundamental object of study in harmonic analysis. They're connected to Fourier multipliers. They're connected to a bunch of things. PDE, they're connected to a bunch of different things in harmonic analysis. And so for those of you, if you're not super familiar with singular integrals, so the prototypical example of a singular integral, and specifically what we would call a Calderón-Zygmund operator, is the Hilbert transform, and it's defined this way: as you integrate the function against x minus y, and there's a 1 over pi factor in front. And to be careful, you have to start by defining this in Schwartz functions to make sure that you have enough decay as you go to infinity so that things are integrable. And then also you need to specify that this is a principal value integral, right? Because you're integrating through a singularity here. And so you need to make sense of that. But for Schwartz functions, this expression actually makes sense. And then you sort of show that it can be extended to other function spaces. So it's well known that the Hilbert transform extends to a bounded operator on LP for P between 1 and infinity. So I already mentioned the Hilbert transform on the circle sort of being the harmonic conjugate operator. And so this is true on the line too. Let me say first that the multi-dimensional analogs of the Hilbert transform in Rn would be the Riesz transforms. I didn't write down the definition of those, but it's sort of what you would expect. And the Hilbert transform is connected to analytic functions because it's whether you do it on the line or the circle, it basically gives you the harmonic conjugate. And it's also connected to signal processing. So this is a very, very important operator. That's a singular integral. And so the Bergman projection isn't exactly a singular integral in the following sense. So if you remember, the Bergman kernel on the disk is 1 over 1 minus w bar z squared. Well, where does that have a singularity? Where is the denominator 0? It's only 0 on the boundary where w equals z. So on the boundary diagonal. And it doesn't blow up at all in the domain. And I'm integrating on the interior of the domain. So in a sense, it isn't a singular integral in sort of this classical sense where you have this singularity on the whole diagonal. But it turns out that you can interpret the Bergman projection as a Calderón-Zygmund operator in a more general sense. And then you can use some of these tools in harmonic analysis that are really helpful. Okay, so I'm going to define a more general notion of a Calderón-Zygmund operator. But to do this, I need to define the notion of a space of homogeneous type. So here's the definition of a space of homogeneous type. So if X mu is a measure space, we suppose that there's some function D X cross X to R that satisfies the following properties. So we're going to require that it's non-negative and that it equals 0 if and only if X equals Y. We're going to require that it's symmetric. And if you look at these first two, you're thinking, hold on, how is this any different from just a metric? Well, it's different because of this third property. The third property says that there exists a constant C, which is bigger than or equal to 1, so that for all x, y, z, and x, we have the distance between x and y is less than or equal to this constant times the distance from x to z plus the distance from z to y. So if this constant is 1, then this is truly a metric. If the constant is greater than 1, we would call this a quasi-metric or pseudometric. And so this notation dxr, I'm just going to use to denote quote unquote the ball in quasi-metric. So I wasn't able to fit the definition on this slide, but so bxr would be the set of y and x so that the distance between x and y is less than r. It's exactly what you expect it would be. And so the other condition of a space of homogeneous type is on the measure, and this is what's called the doubling condition. So we assume that there exists a constant c, greater than 0, so that for all balls, if I look at this inflation of the ball, so inflate it twice, so the measure of the ball, center x, radius 2r, that's controlled by a constant times the measure of the original ball. And that's the so-called doubling condition. And if I have that, then the triple x d mu is called a space of homogeneous type. And the significance of this definition is this is basically exactly the setting you need to do like harmonic analysis with Calderón-Zygmund operators. And this was figured out by Koithman and Weiss a long time ago. But this is the framework we're going to be working in. So now we can define what a Calderón-Zygmund operator is on a space of homogeneous type. And so we say that a linear operator T is a Calderón-Zygmund operator on the space of homogeneous type if first we want to assume that the operator is bounded on L2, and then we also assume it has an associated kernel. So essentially the operator is given by integration against this kernel, and the kernel is defined on the space cross space less the diagonal to C that satisfies the following properties. So the first one is like a size condition. So it says that there exists some constant C1 greater than 0, so that for x not equal to y, we get this estimate. So the measure, the modulus of kxy is controlled by a constant over the measure of a ball centered at x of radius, the distance in the quasi-metric between x and y. So if you think about the Hilbert transform, does this make sense for the Hilbert transform? Well, it does, because the modulus of the Hilbert transform would be like 1 over the modulus of x minus y, and that's the modulus of x minus y is like the measure of a ball. In 1D, a ball would just be an interval, and we're looking at Lebesgue measure. So the measure of a ball centered at x with radius, the distance between x and y, which is just mod x minus y, right? So this holds true in the case of the Hilbert transform, where for the quasi-metric, we just have the ordinary Euclidean metric and the measure is Lebesgue measure, right? So the size estimate basically says that the kernel looks like something like 1 over the measure of a ball. And the second condition is like a smoothness condition, some type of Holder continuity condition. So the second condition says that if there exists some constant C2 greater than 0 and some parameter eta in 0, 1, so that if the distance between x and y is greater than C2 times the distance between x and x prime, well, then if I look at the sum of these kernel differences, so this is sort of just symmetrized so that it holds true in both slots of the kernel. So I look at kxy minus kx prime y plus the modulus of kyx minus kyx prime, and that's controlled by, you can use the same constant over the measure of the same ball, but then you get this factor of dxx prime over dxy to the eta. And you can compute that you have this for the Hilbert transform, but it's a computation, and you would need to do that. But it holds true. And so this is the general notion of a Calderón-Zygmund operator on a space of homogeneous type. Okay, so one advantage so we talked about like all the LP theory. So another question you might ask is about weighted theory for these operators. When are they bounded on weighted Lebesgue spaces? So that's often an important question in harmonic analysis. And so our setting is just going to be, again, a space of homogeneous type, this more general setting than just Euclidean space. And so that we'll say that a weight sigma is a locally integral function that is positive almost everywhere. And we'll define the weighted Lebesgue space in this way. So we'll write LP sigma, and basically it just is the Lebesgue space LP with respect to the measure sigma d mu. And so this is the weighted Lebesgue space. Okay, so the next definition is a really, really important class of weights in harmonic analysis. So if P is between 1 and infinity, we say that sigma is an AP or belongs to what's called the Muckenhaupt class if this following quantity is finite, and this is called the AP characteristic of the weight. And so we take this supremum, and we basically we're taking the supremum over all balls, so over all x and r greater than 0. And what are we looking at? We're looking at the average of the weight on a ball, so that's the first quantity, the first factor here. And then we're looking at the average of some reciprocal power of the weight to the p minus 1. So if p equals 2, this just reduces to the average of the weight times the average of the reciprocal of the weight. And we require that to be finite when we take the supremum over all of these balls in the quasi-metric. And basically what this is saying morally is that the weight is more or less constant on all scales. Let's think about what happens if, in fact, the weight was just a constant. Then this average would just return the constant, right? And then this average would just return, it would return the constant to the minus 1 over p minus 1, but then when I raise that to p minus 1, it will return the reciprocal of the constant, right? And then so when I multiply these, I'll just get 1, which is bounded. And so this sort of extends that notion of a weight being like a constant in terms of this integral sense. And I should mention that we're introducing this in a more general setting in a space of homogeneous type. But if we just think about the Euclidean setting, I could define this with balls, and it turns out that it's the same if I define this with cubes, with averages on cubes. And that's because balls and cubes are geometrically equivalent. You can fit one inside the other, and with a comparable measure is basically the point. So that's that class of weights. And then if we, again, have a space of homogeneous type, we're going to define the following function, which is called the maximal function. And what this maximal function does is it looks at the sort of the worst averages of the function. So if I evaluate the maximal function at z, I take a supremum over all balls that contain the point z of the average of the absolute value of f on that ball. And it turns out that the Muckenhaupt weights, let me go back to this slide. So these weights are precisely the weights for which the Hardy-Loewert maximal function is bounded on weighted P. And the maximal function is very important in harmonic analysis. And it's also a fact, which is important for us, that Calderón Zygmund singular integral operators are bounded on LP sigma if sigma is in this AP class. Okay, so what does this actually have to do with these operators that we've been looking at? So the general moral of the story is that for the Szego projection, the AP class of weights is going to be the right class to study because the Szego projection is like a regular singular integral. But the Bergman projection is a little different. It can be viewed as a singular integral, but sort of the singularity of the kernel isn't inside the domain, it's on the boundary. And so what does this mean? Well, it turns out that there's going to be a certain modified weight class that we consider. So in 1981, Becquelet and Bonamy characterized the weight sigma for which the Bergman projection is bounded on weighted LP for the ball. And we'll say that sigma belongs to the Becquelet-Bonamy class, which we'll call BP on the ball, if this following quantity is finite. And again, this looks like a mouthful, but this is really the same thing as the AP class with a couple modifications. So, or really only one major modification. So again, we're looking at the supremum of the average of the weight on a ball times the average of the weight of the reciprocal power of the weight raised to a power on a ball. And the only difference is that we're looking only at balls B, Z, R, so that R is greater than 1 minus mod Z. Well, what's 1 minus mod Z? That's the distance of Z to the boundary of the ball. So basically, we're looking at weights, we're looking at balls rather, that touch or meet the boundary of our domain. And so this condition really restricts the behavior of the weight near the boundary, as opposed to the AP class, which would sort of restrict it everywhere. So the moral is that we really only care about the behavior, what's happening near the boundary. And so again, this is defined in terms of a space of homogeneous type, these balls. So the balls are given in this following quasi-metric. DZW, which is defined here. So this first piece is the radial distance from Z to W, and the second point is sort of the angular distance between the 2 points. And so you could prove then that the Bergman projection is a Calderón-Zygmund operator with this quasi-metric. And then so actually it would be immediate that it would be bounded on AP, but we can actually prove that it's a little better, that it's bounded on BP. Because AP is going to be strictly contained on BP. And in fact, I'll remark that on the following slide. And that's because we're looking at this supremum over a restrictive, we're taking a supremum over a collection of less objects, right? And so the main theorem is that the Bergman projection B on the unit ball is bounded on this weighted LP space if and only if, it's an if and only if sigma is in BP. And again, the key idea in the proof is to view the Bergman projection as a singular integral operator with respect to the quasi-metric introduced on the previous slide. So they prove that it fulfills that definition that I presented on before. And then you can apply ideas from Calderón-Zygmund theory. And I'll also mention that because the Szego projection on the circle is a singular integral, that's sort of immediate that the Szego projection is bounded on LP sigma of the circle if and only if sigma is in AP. You could say a similar thing for the ball, and in fact you can say a similar thing for other domains. So the general idea is that the AP class is the correct class for the Szego projection, the BP class is the correct class for the Bergman projection. And of course then a natural question is if this technique we have can be applied to domains other than just the ball. So what's special about the ball? And again, this is going to be kind of reviewing things that I already said, but if we're thinking of these in terms of spaces of homogeneous type, AP is strictly contained in BP, because in the definition of the BP class, I'm computing the supremum over a smaller collection of balls, excuse me. And this difference, I mentioned this really reflects the fact that the Bergman kernel is going to be non-singular in the interior of the domain and only blows up at the boundary. And in general, as I said, we expect the AP class to be the appropriate weight class for the Szego projection, and the BP class to be the appropriate class for the Bergman projection. Okay, so what are some results on other domains? So I already talked a little bit about how McNeil viewed the Bergman projection as a Calderón-Zygmund operator. So that means that he showed that it was a Calderón-Zygmund operator on a space of homogeneous type with a particular metric, quasi-metric, that somehow reflects the geometry of the boundary correctly. And so he did this for a bunch of different domains. We won't really worry about the technical details. But this enabled him to prove some unweighted LP bounds in a different way. So the way that we first talked about with the ball with Rudin and Forelli, that use Schur's test. Okay, but this is a different way using the singular integral theory. But it turns out you can take that same singular integral theory that McNeil developed and kind of marry that with the stuff Beckley did on the ball with weights and prove the weighted boundedness of the Bergman projection on when the weight is an appropriate generalization of the BP class on the ball. And this was done by myself, Brett Wick, and Zhenghui Huo at the University of Toledo. And again, you would just define the BP class to be the same as it is on the ball, except you need to define what your metric is. And that's really the point of doing this on any domain. And then, of course, there's a lot of technical stuff that goes into the proof. You need to make sure that certain things that just work for the ball will work on this domain, and that is work, but that's the general picture. And it turns out that you can also do some things for the Bergman and Szego projection on domains with less smoothness. So the Bergman projection, we were able to do it for C4 domains, and for the Szego projection, we were able to get all the way down to C2 domains. And for this, it's more complicated, and you kind of have to use some complex analysis and operator theory techniques due to Lenzani and Stein, in addition to some new ideas. And so this was done by Brett and myself. And I'll also mention, I didn't write this on the slide, but actually Cody Stockdale, who I think is attending the talk, he's a postdoc at Clemson. He and I have worked on this specifically for weak type estimates. So you look at an operator like the Bergman projection is in general not going to be bounded on L1, but it does satisfy a replacement inequality. It's bounded from L1 to this space called weak L1. I won't get into the definition, but this is sort of the behavior that is typical for a Calderón-Zygmund operator. And then you can actually prove that for a lot of these domain classes, the Bergman projection is bounded from weighted L1 to weighted weak L1, and kind of extend the weighted theory that way. And so a couple of further questions, which I think are challenging. I don't know at the moment how to do them. So what if you look at the Bergman projection just on the unit disk? So what are necessary and sufficient conditions for on a pair of weights, omega and sigma, so that the Bergman projection is bounded from L2 with respect to the weight sigma to L2 omega? That's a really hard problem, I think. Or maybe it's easy, maybe there's a more elegant solution that I just haven't found yet. But the two-weight problem for the Hilbert transform, for example, was a very, very difficult problem and very complicated. So I don't know if sort of the Bergman projection simplifies this somewhat, and there are some things you can prove about necessary or sufficient conditions, but getting full necessary and sufficient conditions for this two-weight inequality is difficult. And then the other thing is, you may have realized that I mentioned on the previous slide, we obtained some weighted results for the Bergman projection with BP weights on C4 domains, but we weren't able to get all the way down to C2. And the reason for that was there's some technical obstruction, and it turns out that BP weights don't satisfy what's called a reverse Holder inequality that AP weights do satisfy. So it would be interesting if one could get around this obstruction and prove it for the minimal smoothness case. And there's a lot more questions one could ask about this, but these are just a couple that I thought were interesting. Okay, here are some references: Becquelet's paper, the papers by Lanzani and Stein, the Rudin and Forelli paper, the McNeil paper, Fung and Stein. And thank you. So thanks to Chris Felder for inviting me, all the organizers of OTTER, and thanks to all of you for your attention.
Thank you, Nathan.